Hello, everyone. I was asked to provide an example of how to change the mesh or the mesh dependence. And again, the process is very simple. All what you need to do is basically to change the mesh from a coarse mesh to a finer mesh and see how a certain parameter change. If you see that you have reached a steady state, or that the change is not much, let's say, for example, say 5%, then you know that your solution is no more dependent on the mesh, or basically your mesh solution has converged. So I'll try to do a simple example for you and see how, if hopefully this would be helpful. So I'm going to go to static and structural, and as you know, you can select the material. I'm just going to go directly to geometry, and I'm going to double click to start the space claim and see what's going to happen. So space claim is starting up, as you can see. Just waiting for it to start loading. So you know, and you can of course change the engineering material to whatever material you think is good for you. So I'm zooming this, and then I am going to select this plane. Okay, and then you know all this. Now you're expert. I'm just going to create a cantilever beam, right? So I'm just going to start here. Okay, one of the things that I need to do, of course, is change the space claim just to make sure the units. So let's go to units. And the units are millimeters, so you can change it to meters or keep it as millimeters. And of course, you can change here this. Sorry, what was here? This was millimeter. No, that's too much. So let me go here and say this is say 50. Okay, just for simplicity. Okay, so I'm just going to create a rectangle, and each of these ones is 50. So you see here, basically. Okay, I'm just going to take it 1 meter, almost 1 meter, right? And then you can go and you can pull this thing here. And if you go home, you can pull it for a certain amount just to make it a cantilever beam. So I'm just going to make it 50. Of course, you know that you can type. I showed you all this stuff before, but here I'm just trying to make things simple. Okay, we have a solid. Life is easy. We go here. We go to model. Excellent. In the model, we're going to apply our boundary conditions, and then we can go to solution. So again, things are working here. It's loading, so just give it time for the model to load. So in the model, we have our solid. Just take some time to load, as you can see on the screen. Okay, so this is my model here. What I need to do is to create the mesh and apply the boundary condition. So let us go to, of course, material geometry. I'm not going to touch this. So in the mesh here, you can see here sizing, right? So sizing is default. You can, for example, select, for example, here, coarse. You can see medium and fine. So this is one way of doing it. You can start with a coarse mesh, then medium mesh, or fine mesh. Or you can basically go to element size and you specify the element size. You know that this is 1 meter, for example, and this is 50, right? So let's say we have an element size of 100, right? Of course, my units here, you make sure your units are metric. They are millimeters. So again, here, you can see here, it's 100. So it's 100 millimeters, right? Or you can again go, and one other option is to do coarse, medium, and fine and see if the solution change. There are many options to do this, but let me go with this. So let's do with 100. And then let's basically, of course, there are different methods again for sizing, but I just want to make things simple for you. So generate mesh. So you see here the mesh, and of course I can go here to statistics, and I know the number of elements. So I have 33 elements. Okay, excellent. All right, you can see only one mesh. Perfect. Now we go to static structural analysis, and I'm going to insert fixed. Where's fixed here? Fixed support. Of course, you can fix here, or what you can do is basically you can rotate this. You can basically select that you're going to select the surface here, and then you click, and then you can insert fixed support. Okay, this is one of the things that actually I didn't talk about before. Where do you apply the boundary condition or the load? So you can apply the load to the geometry. I selected a face here and applied to the load to it, or you can apply the load to the finite element. You can apply the load to a node or to an element, right? So it depends. I mean, there is no difference. But the advantage of applying it to the geometry, if I applied it to the face, so if I go and change the number of elements in this face, from example, right now there are only 3 elements to 100 elements, you don't need to change the boundary condition because it's already applied to that face, right? Then I want to again apply some kind of forces. So I'm going to go to this edge, and I'm going to select edge here, and I'm going to select this edge, and then I'm going to insert force. And going back here, the force is not magnetic, it's not order, it is components, and we are walking in the y direction. So I'm going to enter a force in the y direction of negative y direction of minus 2000, let's say, Newton, right? Excellent. This is the force. Now these are my loads. Let me go to the solution, and let's okay, directional. Then I'm going to select the formation in the y-axis. Right? Okay, and then of course you can insert other things, but I'm just going to look into the deflection in this area as my criteria. So let's go and solve solution quickly. That's why I selected only one of these loads. It is still solving, as you can see. Solution is done. Directional solution, right? So of course you see here the most solution, the deflection is here because of the cantilever beam effect. So you can see here that of course everything is in millimeter, and you can find the maximum value is minus 0.006541. Of course, again, you can just select the maximum, or you can see the deflection at one of the nodes or one of the elements, right? But let's assume that my criteria is is this maximum. I just don't want this to be too long for you. I'm sure you will be able to figure it out. So, okay, I just want to make sure that this is my best answer. So I'm going to go to my mesh, and I'm going to change this. Okay, let me make it, for example, 50. Usually you go in small increments, but let me go in 50, right? And you can see here, so I'm just going to go to update. And you can see now, if you go to statistics, I have, for example, now, so when it was 33 elements, it was minus 0.006543. Now it is a 105 elements, and let's see what we are going to get, right? So forces and fixed support, no changes. And then I'm going to solve. So solving again should take longer time, but then I'll go to the direction, right? So you see here minus 0.00655792, right? Again, you can see here there is a change in the value, but how much is the change? You need to set a criteria for you. So you say if the change is less than 1%, then I'm going to basically stop it. If it is 10%, depends on what exactly you want to do. So some people do. So the criteria depends on the solution and what exactly you are looking for. So, but 5% is a reasonable criteria, right? So at 105, this is the value, right? So you need to calculate the difference. You know, you calculate delta and the deflection, and then you do it. And then again, you go and you do the mesh. And for example, let's this time do a 10, right? This is would be a very fine mesh. Update. And then updated. Okay, update. So sorry, updated. So let me see the elements. Wow, this is now 12,000. 625, right? Elements. I'm just taking the number of elements. I'm going to solve. And when it is done, I'm going to look to the directional deflection. It is minus point, wow, 0, 0, 6, 6, 5, 5, 4, right? So you see how is the difference, and then of course you see how the mesh is, and then you take it more until you find it. So let me go, for example, to another mesh, which is here. Let's do it, for example, 8, right? And let me remesh, update, and then let me solve. While it's solving, again, here you have like 27,342 elements, as you can see. But let me go to the solution. It is solving. So you see the solution here is minus 0.00666656, right? So you can calculate. Another way of doing this is you see, okay, if the first 3 significant digits are the same, I'm going to assume that the mesh converge. So there is no specific criteria on doing this. So I'm just going to save this project. I'm just going to call it mesh change, right? And I'm going to host the video for you. So there is no specific criteria. What you can say is, for example, you know, if the first 4 or 5 significant digits are the same from one mesh to another, I'm going to assume that the work is done, or when you know when the difference is 10% or 5%. I would say 5% is very reasonable percentage in error. So if the solution changes in only 5%, this means that the mesh has converged. I hope you find this useful. And if you have any questions, please feel free to email me or text me. Thank you. Okay, hello everyone. So this is one of the lectures to compensate for the issue with answers in the lab. As I told you, I'm going to solve the plate, the famous design plate problem, and show you how to control the mesh and how to use the symmetry. So of course, if you didn't start answers yet, you can go to answers 2022, and then you can scroll down and start answers workbench 2022. Or if you're already in answers, I'm going to start a new project, and I'm going to save this project, which is pretty much the same problem that I was solving before. So we see the answers menu here, and again, this is a static structural problem, so I'm going to click on this, and you can always change the name to plate with hole if you want to do that, or you just keep it. And of course, one of the things that I always advise you to do is to save from time to time. So this is going to be engineering 6290 plate with hole. And this is basically, I'm going to save it in a different place because I'm going on campus today. So I'm going to save it. I'm going to save it in continue on it. Sorry. Yeah. Okay. So plate with a hole. I have the name here. So
this is platewithhole 2, 1. Apparently I have some more, and I'm going to, excellent. So the first thing we're going to do is basically engineering material, and the default material in ANSYS is ANSYS structural. See if I can zoom here so you can see things. No, I cannot. So structural steel is the basic material. You can define your own material or add a different material from the engineering data source. You can see here a lot of material that you can use, general materials, additive manufacturing materials, so on and so forth. For the purpose of this example, we're going to stick with engineering data. Then we need to go to geometry. So when you right click in geometry, you can create the geometry in ANSYS with 3 ways, either using space claim, design modular. This is something new, I think they added, which is new discovery geometry. I didn't use it before. And then, or you can import it from other softwares, right? So space claim is said to be more advanced than design modular, but both of them are good modeling tools. Of course, you have to remember always that ANSYS is a finite element solver. It's not a solid modeler. So you cannot compare the user-friendly, the capability of the geometric creation tools in ANSYS with something like AutoCAD Inventor or SolidWorks, where these are dedicated solid modeling software packages. But you can import from them if you feel more comfortable, or you can basically create your own. So today I'm going to use space claim, hopefully in this, and then in another example I will try to switch to the design, to the modular also, but your textbook is based on new space claim, so I'll try to stick to space claim as much as possible. If you click here, you can see here some information. So I want to go here, and basically in terms of the geometry, we are going to select 2D. Because we are solving the blade problem, which is a standard problem. It's a plane stress problem, okay? And you can always, if you want, get rid of solid body because we are creating surfaces. So if this messes up, you can always click here and go to properties, and it will show. If it is disappeared, you can always bring it back from here. So that's 2D, and I have selected here surface bodies. You can see line bodies if you're solving 1D, or solid bodies, right? So I'm going to keep it that way. Then I'm going to go here, and I'm going to select space claim. So this is going to start another software here, and this software basically are another module, which is the space claim. As these are geometric modeling tools, they really do not affect anything. It is basically a matter of preference on what you want to do with that. So anyway, I'm going to go here. If you right click, select the sketchy plane. I'm going to select the YZ plane, and then I'm going to go to plane view. So you can see here YZ and YX, sorry, and Z is coming out of the plane. So this is my view. One of the very important things that always causes problems in ANSYS is units. You have to make sure that your units are always consistent. So I'm going to go to units, and I'm going to go here millimeters. I want millimeters, so I'm going to stick to that. If you're solving a problem in meters or any other units, you can set it. You can always here control the major, the minor grid, and the spacing, right? So you can make it here, for example, 5, and you make it here 5, right? So basically each grid, major grid is 5 millimeters, and each smaller grid is 1 millimeter. You can always go to snap, and you can snap pixel radius is 1. You know, you can change these things, and you can change them as you move on according to your preference, how easy it is. You'll see now when we create the room. So once we set our units, we are good enough. So basically each of these is 5, and it's divided into 5. Okay, now we are going to create a rectangle, and my rectangle for this case is 100 by 100. You see now some of these are highlighted by blue, so you can type here, okay, and then you can go enter, and then oops, okay, so I messed up. So you can edit, or basically what you can do, you can always delete. So I can go to select, right, using a box, for example, and then click on delete, right? So there's different ways. I'm just trying here to be as clumsy as possible to show you mistakes and how to correct it, but I'm sure you are familiar with these things from other softwares. and basically from other software using your solid modelers. I'm sure you guys are all expert in that. So you can go to 100 and 100 and see it created a square, right? So this is basically, I forgot how to do the ban command, but there is move grid. I think this is the one. No, not this one, sorry. Okay, escape. Okay. Sorry, how do you move this thing back? Home. Yeah, you bring it home, and then you do it plane view again. Okay, that's one way of doing things. We want to create a circle. So in a circle here, you can click on circle, and then of course you can go and you start by clicking the center. You see here, snap to a grid to create the center. One other thing, if you click on the shift, if you bring your cursor here and you click on the shift key, it's going to allow you to locate where your circle is, right? So I can move to 50-50, which is this one here, okay? And basically you can select this as the center. Of course, the problem here, I didn't really click on the 0, 0. You see my point is a little bit away, but this is exactly the center of the square, and my circle here is 40. Okay, so right now what I have a circle and I have a square, I guess. If you click on the escape, this is what you're going to do. So we are going to go to, now this is basically has a thickness of 5 millimeters. So what we need to do is basically we are going to the surface here, are going to pull, and we are going to select this surface, and we should be able to, okay, it's not working, sorry, escape again. I am in the design. Okay, this is another service and this is another service. So I'm going to go to the design. I'm going to click pull, and I'm going to select this, and it should work. For some reason it is not working. Okay, let's see. Okay, why it is not working? This is one of the things. Okay. So pull, this one, it should be working. It is a service. Okay, properties of the service. Thickness, okay, no problem. Okay, so there is some issue here. Let me go back, no worries. Okay, I'll go to home, and I want to take this off this, right? So should we, this command, why this command is not working? Okay, okay. Preview. Okay. Let's select pull. What? Select and drag a face to offset it. Select and drag an edge around it. There. I want to remove material when you pull. Cut. Okay. So yeah. Not working. Okay. Yeah. Okay. One of the things that's happened, which is okay. So let's see now how can we basically cut. Full command should be able. Add to quick access, customize, minimize, okay, display, assembly, repair. No, should be an option to subtract. Okay, okay. This one was working yesterday, so I'm not sure, but anyway, Ansys is not really collaborating. So now you can see different views here. You can go to isometric. Okay, no, I don't want to delete. Delete is going to remove it. I want to basically cut this one. This service, I want to cut it. Okay. Just give me 1 second here. Pull, is pull. And what do you want to do? Cut. Remove material when you pull. Okay. No merge. Control whether a result is merged with the action. Okay. Okay. Mass. Pull both sides. Keep the offset. Yeah. Thicken services. Ah, okay. This one maybe. Okay. So we have a problem. Okay, no problem. We go back, and I can always do this, and then if we go, okay, they are not in a plane now, so that's why, okay, no problem. I can go always and delete this. Go back to this one here, plane view, isometric, and then I can go to, okay, no problem. Always a problem. Delete. Like reboot if you have a problem in your PC, right? So click here, view, home, bottom, top, isometric, and then you go here and you basically select no clip, spin center, sketch, use lots of sketch plane, and okay, and I go to plane view here. Rectangle again. Rectangle is okay. We go to 100 by 100. Okay, and then you zoom in, right, and you go to plane view again. Okay, and the plane view, so we bring it on. Circle, we go in the middle, either we use the shift button or just look at the middle here, which is easy, and go 40. Okay, excellent. Now, what we want to do is we want to go to pull and select this one, right? So, and this should give us a hole, this one, right? And now we go to service, and you can select the thickness is 5. Okay. So we have a surface that is 5 millimeter with a hole. Let me see. Yeah. Okay. So I think the trick to make it is you have to do it while you are in plane view to basically cut the circle out of the plate. Okay. So we have done this, and then you go here in Solid Modeler. It's easier when you create a surface. It's going to ask you for the thickness right away. But anyway, we created our model, so we are good. You can see here tick. You can always go, of course, and edit things, and you delete things, as we're going to see, but we are good. Okay, always save. So I'm going to save. Now we go to the model. Okay. Okay, the process cannot save the file teaching engineering plate file backup because it's being used by another. Okay, don't save. That's fine. We'll go to model. Okay, so in the model, it's going to open another package or another add-on. And this is basically where we are going. You can see it's imported what we have created. Or if you have in here, and you can see here geometry. It's geometry A3, and it is basically a surface, as you can see, and it has a thickness of 5 millimeter. Okay. One of the things also you have to be careful about here are the units, right? So this is millimeters, milliamperes, or you want kilograms, milliamperes. You can, newtons, so millimeters, newton second, so you can select the system of unit that you're going to use. So material, of course, here we have structural steel as our material. We have selected that, and this gives you the information about the material. And you can have more than one material or multi-material in the solution. We'll learn that as we move on. So we go to the fun part, which is mesh. So mesh is basically Very simple. You just here, generate mesh. The easiest thing is to generate mesh, use geometry. This is the mesh that ANSYS have generated. Of course, you have things here like quality of the mesh. You can look to inflation. You can look to statistics, of course. Statistics here, it's 299 nodes and 87, right? You can change. So the default element size is 11.9, right? So the edge here is 11.9. You can change that. So let me, just for sake of changing, make it 8, okay? And then you can go to the mesh. You see old mesh and new mesh. You go to mesh again. Where is it? Where is it? Where is it? And you can generate or you can update mesh. Right? So now you can see here, if I go to statistics, now it's 500 nodes and 140, and we have changed the edge a little bit. Okay, good. We'll come back to this. Now for the load. So this is basically a problem where we have to apply a pressure here on these surfaces, as I showed you in class, if you remember. And this is a standard. I want to see the stress concentration here. So static, structural, insert, and what we are going to insert is pressure, right? And the pressure is, you can use these tools here if you click on them. So this is edge, this is a vertex, this is node element. So I'm going to do to that vertex, and basically pressure normal to surface effect, and the value here. So pressure, when you apply forces, basically force is positive in the x-axis, negative in the positive x-axis, positive in the negative x-axis is negative, and the same thing for y and z. Pressure is positive when it is toward the surface. It is negative if it is away from the surface. So in our case, we are going to put minus, I think 1000. Okay. Okay. Now this is megapascal, right? So megapascal, remember, is basically newtons per meters 10 to the 6 or newtons per millimeter, right? So this is per millimeter. So unit should be consistent all the time. And we are going to apply another pressure. Okay. Where is pressure? Pressure. And we are going to select this edge. You're still in the edge selection mode. So select this edge. And we are going to put here minus 1000, right? Let me go to the units here to see if I can change the units to millimeters. No, I don't have that. That's fine. Okay. So you can see here we have this pressure and we have this pressure here, which is on that. Okay. Sorry, we have one pressure here. Okay. Okay, we have a problem. Pressure 2 is applied here. Okay, so no problem. I can always delete, just to show you again, and I can always delete. Excellent. Okay, now we go again. Static, we can go from here and insert pressure. You can select edge, and you can select this edge, and you can put here minus 1000. Let's make it 1000. I think 1000 is too much, but anyway, apply. So this is pressure here, minus 1000. Then you can go to this edge here, and you can click on insert, right? You don't have to do it from the side menu. And you can put again pressure minus 1000, and you can go here on geometry selection, yes, this one here, and then you can go to apply, right? So we have a pressure. So we have two pressures now, here and here. Excellent. What do you want to see? We want to see, if you go to solution, insert, we want to see deformation. So we can ask for total deformation. We can ask for directional deformation. So directional deformation in which axis? In this axis, which is the x-axis. We're good. You can ask for stresses. So let's go to equivalent von Mises stress. Whatever you can ask for. We're done. Okay, let's solve. So you see the solution here. Okay, solver warning or error have been encountered. Okay, where can I see the messages? Here. Okay, Solver error or warning have been encountered during the solution. This is usually a result of an ill conditioned matrix, numerical, remember, possibly due to unreasonable material properties, an under constrained model, or contact related issue. Check results carefully. That's if you solve. But of course, you see here the solution. So this is basically the rigid but ill condition means it's not well constrained, and as mentioned here. So this is a problem for us. So you have to think about a way because this thing is moving when you do the analysis. So one of the ways to do things here is basically to apply a constraint. But the problem is if you, for example, constrain this edge or this edge, you are basically changing the nature of the problem. So one of the things that you can do, if you go to model, you can basically insert something called name selection, right? And you can give it a name here. So rename, I'm going to call it node 1, right? And then I'm going to go to model, insert selection, and I'm going to call it, rename it to node 2. Excellent. Now I can go to constraints and I'm going to insert and I'm going to select nodal displacement. Okay, nodal displacement. And I'm going to go here. One of these options is elements, and this one is node. You're going to see the mesh. I'm going to constrain this node. Right, so it tells you here named selection and X component. I'm going to make it here 0. Right, there is no movement in X or Y. And I'm going to select named selection. So you can select to node number 1. Okay, and then you enter or you apply, node number 1, right? And here 0, it should be good, right? You can see here nodal displacement, and then you go again, insert nodal displacement. When you're applying to the node, you are not applying things now to the finite element model. You're applying things to the finite element mesh. So here's nodal displacement. Node number 2, node number 1, and you enter. It should accept it. Why it's not accepting it? Okay. 0, node 1. Delete. Okay, again, insert nodal displacement, and you go and you pick up node option, and you select this node. Okay, so name the selection. You're going to select node number 1, and you're going to say it is 0, and it is 0, and enter. Why it is not working? Okay, click again. Oh man, what's going on? Node 1, 0, 0. Okay, no problem. Here. Oh, that's the same thing. Insert again. Okay. Nodal displacement. And I'm going to select this node. And I'm going to select node number 2. And I'm going to put 0 and 0. Okay. Why it is not accepting that? So node 1, node number 2, node 1. Okay. Selection. I'm gonna save this, and I'm going to come back to it. Okay, why it is not working? That's a $1 million question. Yeah, node 1, displacement, coordinate, nodal coordinate, 0, 0, 0. Press. Excellent. Should be okay. Okay. Anyway, I'm worried why we have this these ones, but let's see. Invalid name selection. Okay. Invalid name selection. Why invalid name selection? Okay, so the name selections are not good. Okay. Invalid name selection. Why? Name selection. Okay, that's not. Okay, delete. Delete. Yes, you want this object? Yes, I want to delete it. And of course, nodal displacement here is deleted. And nodal displacement here is deleted. That's right. Happens all the time. Murphy's law. Okay, so I go to model, I go insert name selection. Okay, I'm going to keep it like this, and then name selection. I'm going to select node, and I'm going to go this is node. Okay. Apply. So node 1, okay, which is this one. So I'm going to rename it now, and I'm going to call it node 1. Okay, now we go to this one, named selection, and I'm going to go here again for node and pick this node. And I'm going to go here and apply. Node number 2, excellent. Okay, things are brightening up. Insert nodal displacement, and nodal displacement here, named nodal displacement. Okay, insert nodal displacement, named selection, node number 1. And if I go to definition here, it's going to be 0, and it's going to be 0. Right? And enter. Zero. Okay. Nodal displacement 2. Okay. Now we go to nodal displacement 1, which is I'm going to again selection. I'm going to select selection because we didn't call it, and we're going to call it 0, and we're going to call it 0. And we should be okay. Now you see the click here. This means it's working. Now let's quickly solve and keep our fingers crossed, of course. Yes, solution is going on, and now we see total deformation, right? Directional and stresses, as you see here, of course, the stress concentration. It is more at the nodes, of course, here, but you can see here the mesh is not really smooth, right? You see these edges and everything, which is not good. So now we learned about the refinement of the mesh, and we are going to do that in the next step, and then we move to symmetry. So let me save here. Okay, so now let's play with the mesh a little bit. So if we go back to mesh, right? As we saw, the mesh is not really, the results, they don't look like continuous or smooth, right? So we can do a lot of things, right? So we're interested more in the stress concentration area here. So one of the things we can do is we can go to mesh, insert sizing, and as you can see here, selecting of geometry. So I'm going to go to edge, and I'm going to select this edge. And in this edge, basically, which is of course you can select the geometry and you can apply. You see here the mesh. Okay, I want to change it a little bit. So element size, instead of 8, I'm going to make it 2, for example, or 3, right? And of course, when you do any changes to the mesh, a lot of problems are going to happen. First problem is you have to remesh, update, right? So this is my new mesh. Second problem now are these points are no longer valid because when we selected the nodes, we selected from the old mesh, right? So now these are not going to be valid, right? So basically, if you go to this node here, right, selection, we have to insert our new node. So we go here, it's going to show the mesh, sorry, mesh, and I'm going to select a new node for it, right? And basically apply. So now it is good, right? I go to node number 2, and I'm going to select again this node, and I'm going to apply, which I didn't do before. So these are the new nodes, and you see here also these are changing. So now the nodal constraints are on the new node, because when you change the mesh, things have changed. If I go now to the mesh size, I don't remember if you still remember, but now we have 404 element, we have 1300 nodes. Before we used to have 500 nodes, yes, and maybe 200 elements. You should keep this. So nothing is changed here in terms of this. So I go back to solution, and I'm going to solve again. Right, and you can see here the tick mark, so total deformation, directional deformation in the x-axis. You see the variation along the x-axis, and then equivalent stresses. You see now, if you zoom, you see a smoother surface. You can, refine the mesh more, like you see, get a finer mesh, but if you want to, but I mean, you can play with that. Of course, you have to monitor the solution, of course, total deformation, directional deformation, and see how does it change with the mesh size to basically perform to make sure that your solution is independent of the mesh. Of course, I think in ANSYS, but this is an advanced feature, you can do mesh sensitivity analysis. Maybe we'll investigate that later on. So another thing that you can do, let's say, for example, you want the mesh to be controlled along one of the edges. So again, if I go to mesh, which is this one, okay, insert sizing, and I'm going to select one edge. Where is that edge selection? I'm going to select this edge, okay, for sake of administration. I mean, so this is edge. Okay, so this is a good feature. Bias. Okay, so capture proximity. No, I want this one. So you see here, no bias means distribute the edge as you see here. But see here, for example, if you select this one, you can see here it's smaller in the middle and larger at the bottom, or you can select the shape of bias. So basically, it does not divide the edge exactly equally. Sorry, equally. So you can select here smaller at this edge and then smaller at this edge, and then also you have to select the bias factor. So basically, the bias factor. Let's select one, and then this is a reverse bias. So if you divided the smaller edge element here, larger element here, you can reverse it. So smaller elements would be this size, and larger elements would be on the other side, right? So basically, geometry. We already selected the geometry here, which is the edge. So if I click here, you can apply, and here you can see the element is done. So we can do that, and then we can where's mesh? Yeah, obsolete mesh, of course, and then you can update the mesh or regenerate the mesh. Right. So actually nothing happened here because of the selection, but you can basically go back here, edge sizing. I want to select something that is more helpful, but here apparently it does not. And this sizing factor, I'm trying to figure what it is, but I don't. Oh, yeah. Okay, so the sizing factor now changes. You see here, the size of the element is not the same. Okay, so apply. And then whenever you do changes to the mesh, you have to, of course, update. And then as you update, of course, here the selections are going to be different because numbering of the nodes are different. We have more nodes now. So let me go to mesh quickly and let's see what we have. Now we have 396 element and 1294 nodes. Before it was 11 something, right? So again, I have to go here and I have to pick a node and then you select this node, right? Select a node here, you can zoom of course on the node, right? And you can go to apply and then go to the next one. And as you can see here, this is now X because this is a sheet of this node that the ANSYS doesn't know what it is. Now if I go to this node, okay, and then you can go here and apply, everything is corrected. Okay, for that error, you might go ahead with only one node and it will save you. It might be 2 nodes, 3 nodes, depends on the geometry and what exactly you are doing. Okay, so solve. And the solution here again. And then again, you can go here, the solution data information, you'll find all the information about the meshes, about the time, number of elements, so on and so forth. You go to total deformation, you go to directional deformation, and you go to equivalent stresses, right? And again, you can play with the meshes as you see fit. Okay, so this is basically plane stress. I think in this basically video you learned about how to control the mesh or some of the features. There are other features, of course, here that you can learn or you discover when you do. So basically you can refinement, face meshing, mesh copy, inflation, weld. There is a lot of things that basically you can explore when you solve the problem, when you solve different problems or projects, and you know how to create the insert named selection, so you can specify a certain node. I think also you can see this here. You need that named selection when you want to create something like a probe, or you want to see the deformation at certain nodes or certain location in the mesh, right? And then you know how to solve. So hopefully this is a good start. Now we want to use symmetry. This is the symmetric part about the X and Y axis. So we want to use symmetry. So we go again to here, and we are going now to insert another static analysis. This is a project, so it can have many analyses as we want, as we're going to see and learn. So static structure, I'm going to call it plate with hole slash symmetry. Okay, so material is pretty much the same. Geometry, I'm going to make sure that the geometry is what I want, which is basically 2D, right? And again, you can access this from here for properties. So surface solid, no problem. 2D, that's the most important thing. And then we go to our famous, lovely space claim. Okay, you can do the same thing again in space claim. You can do it in designer modeler, or you can import from another software. Of course, importing allow you to use a more advanced solid modeler, but also it comes with some problems, right? It's not easy. There are some issues and challenges. So again, you guys know the drill, I guess by now. Select the sketchy plane, which is this one, and then plane view. Go and play with my units. It should be the same from last time, but if it is not, because I did it a lot of times, so I think it is smart enough to do it. Okay, the grid size here is going to be, I'm going to make it 5, and I'm going to make 5, okay, and this is all optional, of course. Okay, so what we want now is to create a quarter part. So what I'm going to do, I'm going to create a rectangle again, or you can create it with line, by the way. So the rectangle is 50-50, okay, 50-50, yeah, okay, right, because it was 100 by 100. And I'm going to create a circle. The circle is at the center here, and the diameter is 40, right? Okay, so we go here, and the circle. Okay, no, skip. I didn't want that circle. Let's see how Bull is going to do it. Pull and okay, service. Okay, and pull. Okay, yeah, same problem. No, I don't want to activate subway physics. What happened? What happened? What happened? Kill this one. It's always a problem for me. Thickness, yeah, service, sorry. Thickness is 5. And enter. So where are we? Oh, sorry, let's move. Okay, go back, pull. Yeah, this one. Thickness service. Okay, thickness service. Service. 5. Yeah, 5, sorry, 5 millimeters. 5, okay. Execute the command. Service, 5 millimeters. Okay. Pull. Okay. 5 millimeters. Okay. When this option is on, the service is extra. Okay. Select the whole thing. No. No. What's going on here? No. Service 5 millimeters. Okay. Let's delete this. Let's delete this. Okay. Service 5 millimeters. So I have a service that's 5 millimeter. I'm not sure what's going on here, but I have to check this command. But anyway, we created our service. Okay, for the sake of this, you guys can struggle with this. I'm sure you'll figure it out. Okay, so geometry is done. We go now to model. So we have our model. Okay, so again, geometry is given. Material, we can change the material if we want, but we are using exactly the same material, structural steel. We're good. We go to mesh, and we are going to just generate a mesh. Okay, so now what we need to do, we need to apply the load here. We need to apply till there is the symmetry condition. So we go to geometry, I think here, no, sorry. Okay, let's go to static structure, insert, pressure, and we are going to go, as you guys know now, H, and we are going to select here minus 1000 because it's per millimeter, right? So we're not changing anything. Apply, and I think we're going to go to model, insert, symmetry, right? So here symmetry, insert, symmetric region. So this is about the x-axis. Which side is about the x-axis? This is the x-axis. So symmetry about the x-axis means this edge here, right? And then you apply. So this is symmetry condition. And then you go to model, insert, where is it? Model. Where did it go? Symmetry, insert, symmetry region. Again, you go to symmetry, you can insert another one. And we are going to select this edge. And this edge is above the y-axis. So we change it. Right? And you go here and you apply. So we have two symmetry conditions. This one, this one. We have a nice mesh that, of course, where's my mesh? There is my mesh. My mesh is here. You can go to statistics and you can see the sizes as we did last time. Last time it was 8, right? If you remember when we started with an 8 element. So I'm going to go with 8 here, right? So refresh the mesh. Right? Okay, so we are good. Solution, we are going to add a lot of solutions here. So deformation total, directional, all the good stuff, and then foam meshes. Of course, you can add strain, you can add different kind of stresses, and then we are going to solve. Solution is very quick, of course, because the number of elements is quarter of the last time. So you see here again, this is the stresses. This is again the stresses. If you look to, of course, you can always go, which is the beauty of having this. You can compare. You can see the result. These results. You can start it here, so you can see the results here, and you can see the results, here. Right? You can compare them. But of course, when you compare them, you have to make sure that you have the same mesh size and the same directions. But again, you can see here the mesh, of course, is final. It didn't take much time. You can do whatever mesh refinement you want here. So you can insert, for example, sizing, and you can go and select this edge, for example, and you can go here to the element size and make it, I think we made it 2 last time, and then here you can apply. So this is basically, there is no bias here. Of course, you can do the bias to change the variation along. And then once you do that, you can go to mesh and you can update your mesh. And once you update your mesh, of course, we didn't face the rigid body motion, remember? That's one thing. So this is one of the advantage of using symmetry. You already constrain the solution much better. You don't need to add the rigid body motion. So solution is done. So you can see here the deformation. The mesh is much better, directional, and so on. So again, what I want you to do now, based on this example, I want you to go make sure, for example, if you select 10,000 nodes for the full element, you take 2,500, which is quarter, and see how the results compare. And also, I want you to play with the mesh and basically see how the results are dependent on the mesh. Okay. One of the things that I didn't do when I go in here, of course, is I have to check the units, because sometimes the units are in kilograms and grams. So you have to make sure that basically your units are consistent. I hope you find this useful. So the purpose of this exercise was to show you some of the mesh control, show you the rigid body motion, and show you the use of symmetry. Of course, we didn't have to use the symmetry for both. You can decide, for example, I want only to create half of it and use symmetry about only one axis. Okay, you can, of course, here go to these graphics, show it to people who don't know what's finite element analysis, and wow, you are creating, rocket science, but it is not really rocket science. It is graphical. One of the things also that you need to keep in mind here when you look to these results, this is graphical representation. So, the values here, you see what is the deflection here? The value of the deflection, the maximum value of the deflection is 0.5 millimeter, right? Which is basically, it might look huge here with this red number, but you have to look to the numbers, because this is graphical representations. Okay. So again, you can create more than one project. So basically, you can select different kind of materials. For geometry, you can use different types of ways to generate geometries. And then in the model, you apply your loads, your boundary conditions. In the solution, you see the solution and the results. We are going to basically, next time, we're going to use this example to optimize it. When we talk about optimization, we'll add an optimization technique here. And also, we are going to use this for the next video, which is thermal structural, or one of the other videos or lectures is the thermal structural. And in the thermal structural, basically, we are going to use a steady state, we are going to use transient structural, and then also we can use optimization. We will see how we can do that. If you are using the same geometry, you can always have a different model and a different solution connected to this one, right? So I'm just going to show you here, but I'm not going to do anything. If I want to do, for example, thermal analysis that use the same geometry. So I go here, and basically what it tells the ANSYS, use the same engineering material, use the same geometry. I'm just going to change the model, and I'm going to change the other stuff, right? So of course I'm stuck here as I don't know how to delete this. There should be a way to delete it, which is this way. So we're going to learn about it. So again, save. Always remember to save your work because these are very huge file, and all of a sudden the system will crash. I hope you find this useful, and if you have any questions, please let me know. Thank you.